In today's lesson, we're going to be looking at Descartes' Rule of Signs. Using Descartes' Rule of Signs, what we can get is a breakdown of the possible number of positive real roots a polynomial has, and a list of the possible number of negative real roots a polynomial has. To find this out, what you do is you take your polynomial, in this case p at x, and you count the number of sign changes that occur in the polynomial. So you'd list the polynomial in descending order by exponents. So for instance, let's say you have your polynomial p at x, and you can see here I've listed this polynomial in descending order by the exponents. And you can see here, right here, I have a sign change. We went from positive to negative, that's a sign change, and then we went from negative to positive. So this would count as two sign changes. So that would imply, using Descartes' rule of signs, we have two sign changes. And then what you do is you keep subtracting 2 until you get to 0. So in this case here, I've got my polynomial p at x. I've listed it in descending order by the exponents. I've got a sign change from positive to negative back to positive. That counts as two sign changes, and you keep subtracting 2 until you get to 0. So in this case here, the first subtraction gets us to 0. So therefore, this polynomial I've created has either two positive real roots or no positive real roots. Likewise, find the number of negative real roots, evaluate this polynomial at negative x. So I'm going to use the same polynomial here. If I evaluate this at negative x, we get the following. That's one sign change, still negative, and two sign changes. So we've got two sign changes here for this one as well. So this is going to be either 2, and again, just like before, you keep subtracting 2 until you get to 0. In this case, 2 and 0, and we're done. So therefore, the number of negative real roots is either 2 or 0. So now we have a better way of looking when you're going through synthetic division. You now know like some breakdown of how many positive real roots and how many negative real roots a particular polynomial has. Let's take a look at some more examples using Descartes' rule of sign. So for the following example here, I want to examine Descartes' rule of signs. You'll see here we're going positive. We have a sign change here, and that's it. So there's only one sign change here. So that using Descartes' rule of signs, and you can see right away, we're taking a look at the finer point of the definition here. I've got one real root. Descartes' rule of signs keeps subtracting 2 until you get to 0. In this case here, I subtract 2, I go right to -1. So you would stop here, and this is your only answer. So I know that this polynomial has exactly one positive real root. Okay, let's take a look at the number of negative real roots. So again, we evaluate the polynomial now at negative x, giving us, and calculate the number of sign changes here. We have a sign change here, positive to negative to positive, and then positive to negative again. So this has 3 sign changes. So the number of negative real roots that we have for this polynomial is either going to be 3, and then again you subtract 2 here, so it's going to be 3 or 1, and then that is it. So once again, you stop. You don't once you subtract 2, you don't look at negative values. So therefore, the number of negative real roots is either 3 or 1. So to summarize this polynomial p at x has exactly one positive real root, one negative real root, or one positive real root and 3 negative real roots. So the possible breakdowns of this polynomial would be p at x can either have one positive real root and one negative real root. But now the degree of the polynomial is 4. That must mean the other 2 roots must be complex. Or I have one positive real root and 3 negative real roots. And again, there would be no complex there. Okay, so using Descartes' rule of signs, you can be more specific in terms of the possible root systems you can have here. Like we said, as we go through these, it's a quick check, and it adds a little more detail to your root systems and outcomes that you can have. Let's take a look at another example. In the next example here, same idea. I want to go ahead and use Descartes' rule of signs. So for p at x here, I have one sign change, 2 sign changes, 3 sign changes. In this case, I have 4 sign changes. So number of positive real roots are, so you're going to have 4, 2, or 0 for the number of positive real roots. Let's take a look at p at negative x. Evaluating p at negative x, we get the following. And evaluating p at negative x, we get 0 sign changes. So the number of negative real roots here is 0. So therefore, my polynomial here of degree 4 either has 4, 2, or 0 positive real roots and does not have any negative real roots. So again, if you want to break this question down, you want to use your rational root test, you want to start doing synthetic division to find a root, I do not have to look anywhere in the negatives. I know it doesn't have any negative real roots, so that cuts your workload in half. And then I can kind of go through this decomposition here. So the possible outcomes for my polynomial p at x are as follows. And these are our options here. Either you have all real roots and they're all positive, or you have 2 real roots which are positive and 2 complex, or you have 4 complex roots. And those are your outline breakdown for this one. And that's the root system possibilities for this polynomial. Let's take a look at another example. So following example here, same idea. We want to calculate the number of sign changes. I have exactly 1 sign change here. The number of positive real roots is exactly 1. Valuing this at p at negative x, we get the following. And examining the number of sign changes here, we have 1 sign change, 2 sign changes. So either you're going to have 2 sign changes or 0 sign changes for this one here. So for our polynomial p at x, we have the following possibilities. Now, if you look at the root system for this polynomial, we have 1 positive real root. Now, either you're going to have 0 negative real roots, which would mean I cannot have 4 complex real roots as the degree is 4, and I can't have no complex real roots because I just have the 1 here. So it must be the case here that this is going to yield 2 complex roots. And that third root, in case you're wondering, it's x equals 0. And you can see that here. So x equals 0 is neither positive or negative in this situation. So what we're looking at here is the possible breakdown for this is there's going to be a root at 0, but using Descartes' rule of signs, the number of roots that are greater than 0 will be exactly 1, and the other breakdown must be complex. The other situation here is we have, again, 1 positive real root, as we know, and again, you have to have a root at 0, and the other option is 2 negative real roots. So again, we do have the polynomial has a root at 0, and then we know that it has to have exactly 1 positive real root, and then the other 2 roots must be negative. Let's take a look at another example. In this example here, same idea, we want to look at the root system of the following polynomial. When you write down your polynomial, you write it by descending order by the exponents. So in this case here, anything that has a 0 coefficient in front isn't listed. We don't consider that for sign changes. So in this situation here, we're going from positive to negative once. This is exactly 1 sign change. So the number of positive real roots is exactly 1. And evaluating this at negative x, we get the following. And the number of negative real roots is either 2 or 0. So you have the following decomposition here. Either there's exactly 1 positive real root, or there's 2 negative real roots, or no negative real roots. So the following decomposition for my polynomial p at x is as follows. 1 positive real root and 2 complex roots, or you can have 1 positive real root and 2 negative real roots. All right, that concludes today's lesson on Descartes' Rule of Signs.